15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Here we go again. Hello and welcome to the Space Nuts podcast, episode 210. I'm Andrew Dunkley, your host, and with me as always is the better half of the Space Nuts podcast, Professor Fred Watson. Hello, Fred.
Hi, Andrew. Yep, I'm not sure I'm the better half, but I make my contribution.
But you tell people what they want to hear, which is more than I can do. I'm just the pretty face.
Oh, really?
Well, you can't see me anymore because we don't do this on the old platform, so you can't see how stunning I turn out.
So something's changed, has it?
No, not really. It's just,
all right, sorry about
talking
that.
garbage.
Yeah.
No, it's all right. Now, coming up, we're going to talk. This is a really interesting story, an asteroid moon. This is a moon that's going around an asteroid. They've had to give it a name, and they've given it a name for a very odd reason. We will explain very, very soon. There's also a new exoplanet that you might have read about in the news on the weekend. This one was recently discovered. It is unique. It's unlike any other exoplanet that's been found so far. So what's unique about it? Well, we're going to tell you. And we're going to answer some questions from the audience. John Carter wants to know if it's possible to put a number on the things in space. How many stars, how many planets, how many galaxies, to the nearest 0.01. We'll try and answer that. And Ben Harper has messaged us to say, can a black hole form without a star? That is a fascinating question, Ben, and we don't know, so we're not going to do it. But we will. But let's start with this asteroid moon. Now, this, Fred, is there's an asteroid out there. It's got a name. It's going somewhere. It's going to pass near Earth, and it's got a moon that's orbiting the asteroid. Now, the moon is nameless, but they've got to give it a name because of what they're going to do next.
Indeed, exactly as you've said, this is an extraordinary story. So it all comes back to the idea of the fact that we expect the Earth to be potentially impacted by asteroids. It's been impacted by asteroids throughout its whole history, and we now have the technology to try and forecast when that might happen with all these telescopes that are, like Pan-STARRS and other telescopes which are surveying the sky for near-Earth objects. But the question is always, okay, so you find something that's going to hit the Earth in 30 years, what do you do about it? And the glib answer is, well, we deflect it slightly. We provide an acceleration to it, either by, knocking it slightly with something or putting a rocket motor on it or whatever. And 30 years later,
you build a giant cricket bat.
A cricket bat
and launch it into space.
Yep.
And I say cricket bat because I know they play baseball in America, but you'd probably miss with a baseball bat. So,
depends how good you were.
Cricket bat's better chance.
Yeah. So whatever, there's a dozen technologies that you could use to deflect an asteroid, we believe, and then the orbit changes sufficiently that it misses the Earth. That's the idea. That's the whole principle of what you might call civil defence as far as Earth asteroids are concerned, or actually more like quasi-military defence, I guess it is, because you're going to basically move something. All right. So how do you test this? Well, we've not really been able to test it to date, but there is a NASA mission which will launch in July next year, July 2021. So we're just a year out from the launch of this. It is called DART, which is a really nice acronym for Double Asteroid Redirection Test. And
they've done well.
Tells you the story. Yeah, it's great.
Yes.
It's a really good one. So that in itself tells you the story as well, because the object which is going to be moved is the moon of an asteroid whose number I think is 65803, just to give you something in there. So this is a double asteroid, effectively. And there are quite a number of examples of that, where you've got a larger asteroid with a smaller one going around it. So in this case, we've got an asteroid which is a substantial size, measured, I think, in kilometers, but it has this moon whose diameter is not that well known because it's so far away, but it is in the order of, I think it's 100, if I remember rightly, about 160 meters in diameter. So the idea is that DART will launch, as I said, next year, head off to this pair of asteroids and clout the smaller one. It's going to basically crash land into it a bit more than a year later, September 2022. Its distance will be something like 11 million kilometers from Earth, which is relatively local. In fact, this is a fairly nearby asteroid. Although the pair of asteroids we're talking about apparently could never threaten the Earth, just because their orbits are not. The orbit is not like that. But okay, so you hit the moon, and what that is expected to do is to change the orbit of the moon around its parent asteroid, which I haven't told you. Sorry, it's called Didymos.
Okay.
Didymos. That's the name of the main asteroid. Basically, you change the orbit of the moon around its parent body, Didymos, and that is a much easier change to detect and measure than taking a single asteroid and giving it a clout to try and move it into a slightly different orbit around the sun, because you don't know that you've managed to do that for years, probably, until you can accurately measure the change in its orbit. If you go for a double asteroid, it's a very clever idea. Go for a double asteroid and hit the smaller one, then you'll be able to measure the change in its orbit almost immediately. So you know exactly whether you've had any effect, whether it has been a success. Really very, very neat science. The orbit of sorry, go on.
They're not trying to knock the small one out of the orbit of the big one. They're just trying to alter its orbit so it alters the direction of the bigger asteroid.
No, it's not even that, Andrew. Oh. It's only altering the orbit of the moon around the parent asteroid.
Okay.
So the orbit of the moon. We haven't got to the naming yet, but we will in a minute. The orbit of moon around Didymos is once every 12 hours. So the expectation is that with the DART spacecraft, you'll probably put a change in the orbital period. It'll tighten up and it'll be reduced by 10 to 20 minutes. And that is very easy to observe. So you're not affecting the the parent body at all. You're just affecting the orbit of the moon around it.
So the moon will have a slightly faster orbit as a consequence of the impact.
Yeah, and it's that you can measure. So you know how much energy you've put into it with this spacecraft. Excuse me, I've got the typical morning frog in the throat here. You know how much energy you've put into it, and then you can measure what its effect is, and you can do that actually immediately. You'll see a change in its orbit because this moon is, as I said, it's so small. It's as I mentioned, 160 meters across, and it is a fantastic idea. There is a plan then for the European Space Agency to send a probe actually to the moon whose orbit has been changed in 2024 to make sure that the change in orbit is permanent. That's the idea, to make observations that confirm it. So
why did they have to give it a name?
Because they had to give it a name just so that they knew. You can't keep saying it's the moon of Didymos. Although it did have a nickname, which was the Diddy Moon for a while, which kind of goes back to a comedian who used to work in in the UK when I was a youngster, who his name was Ken Dodd, and he invented the Diddy Men. And the Diddy Men, everybody was mad on the Diddy Men. So the Diddy Moon is the nickname for it, but that's not a very nice name for it. So you do need to have something that you're going to talk about when you're clouting it with with a rocket, and that's why the International Astronomical Union has been engaged, because they're the only body in the world that can name objects in space, and so they were approached and said, yes, we'll give it a name, and it is being called Dimorphos, or Dimorphos.
Ooh.
Probably Dimorphos, and it's a Greek word meaning having two forms, and the two forms are the orbit that it had to start with, and the orbit it will have after it's been knocked askew by the spacecraft DART. So it's really, it's a really interesting idea. So Dimorphos, or Dimorphos, depending on how you pronounce it, is something that will be very much in the news from the middle of next year until late the following year, because we are to some extent staking our abilities to change the orbits of asteroids on this experiment. So it could be very important for the future of our planet. Protecting us from incoming asteroids, near-Earth asteroids that might have a disastrous effect on the Earth. If we can shift their orbits, and this is the first experiment to determine that, if we can do that, then we're in better shape than we were before.
Yes, indeed. I'm sure they've done their calculations, but do we know how hard they're going to hit it?
No, I don't know offhand, but yes, you're absolutely right. The impact velocity will be extremely well known.
I imagine they're going to hit it at like thousands of kilometres an hour or something to that effect.
I suspect, I'm not sure about this, but reading between the lines, I believe that they will basically, there won't be any slowing down to go into orbit around this thing. They'll just, on its incoming trajectory from Earth, they'll just slam straight into it. Yeah, because that will give them the highest velocity impact.
Yeah. Gosh, okay, so it'll be there won't be any bells and whistles on this spacecraft, I imagine.
That's right.
You don't need any extras, just a battering ram at one end and a rocket at the other, with a guidance system.
Yeah, I don't know what its mass is, but we can follow up on that. That'll be easy to find out. But it's a great story, isn't it? That we've got a new moon that's going to be moved.
Yes. Well, it'll be interesting to see how it turns out. I hope they don't miss. But even if they did, it would teach them something. That's what this is all about. If they succeed, great. If they don't, then they'll go, okay, we need to reanalyze the way we're doing this so that when we have to do it for real, we don't miss. I don't think they will miss, but I'm just throwing it up there because that's that's the way I am.
It is, yeah. If you can fly by something like Arrokoth, 6 billion kilometers away, and pass it within the exact distance that you predict and take all the photographs, that's what we used to call Ultima Thule. I think you can do something only 11 million kilometers away. It's on our doorstep, really.
Yeah.
Easy peasy, Andrew. Easy peasy.
Like shelling peas.
Yeah,
exactly. All right. Well, that's a story we'll be very keen to follow up in about a year or so.
Yeah.
You're listening to the Space Nuts podcast with Andrew Dunkley and, of course, Professor Fred Watson.
3, 2, 1.
Space Nuts.
As always, I want to send a special shout out to our patrons who support us financially. Some have mortgaged their penthouses in New York to just send us a few dollars so that we can stay operational. It's actually not quite that expensive. Fred's salary is, but I get the change. But if you would like to support us financially, it's an option. It's not something we ever would tell you to do. We can only throw the idea up there, and it's certainly your choice. I mean, you can still get the podcast without having to do it. But some people approached us and said, we'd like to give a little bit back because we love what you do, and we love that you love what we do. And there are a couple of options these days. You can go to Supercast, and you can set up a bundle service, depending on what sort of combination of things you want to listen to. You can have Space Nuts and Space Time, or Space Nuts and Dark Sky projects or conversations, and so on. There are all sorts of options. That's at bitesnetwork.supercast.tech. You can also do it through Patreon. And Fred, we've had a few more people sign up to Patreon this week, so welcome aboard. And that's at patreon.com/spacenuts if you would like to support us that way. And of course, the benefit of being a patron is you get bonus material, and we will be providing some bonus content this week. So that's all coming up. And thank you for being a patron in whatever form you choose. Now, Fred, let's move on to this really interesting discovery. This is an exoplanet. We've had quite a few exoplanets to talk about lately, but this one, it's not very far from Earth, but it's unique. They have never seen one like it before. I know we're in the early phases of exoplanet discovery, and we're finding more and more, and the numbers are getting up into the thousands now. But this one is one that isn't like any other that's ever been seen so far. And it has been suggested that it may well be a unique discovery. So what have we got?
Yeah, I bet it's not unique in terms of the existence of these things outside in the wider universe. But as you're up,
I knew you would say that.
You're absolutely right. It is unique to our knowledge. There you are. That's the way to put it.
That's
and you did say it's a unique discovery, and I think that's absolutely right. I should explain, Andrew, that I'm very. I'm always very careful with the word unique, because I once got picked up on a radio show by somebody who I said that something was very unique, and I got hammered by this listener who said you cannot quantify.
Would have been the ABC for sure.
It was the ABC, yeah.
Yeah.
You can't quantify the word unique. You're either unique or you're not, and you can't put a
exactly. Yeah.
So there you go. So. We are agreed, I think, that this is a unique discovery, but it might not be unique in the universe. So, having got that point sorted out, let's move on to this very exciting discovery. It is, relatively nearby, 730 light years away. This is a sun-like star, so you would expect, maybe a solar system-like solar system around it, but not at all. What was discovered, and again, this is a discovery that comes from TESS, the Terrestrial Exoplanet Survey Satellite or spacecraft. TESS is, what did I say? Transiting Exoplanet Survey Satellite. I can't remember what I said, but I'm sure that wasn't it. Transiting Exoplanet Survey Satellite, which looks for the dips in the intensity of stars as a planet passes in front of them. And so this particular object, which actually rejoices in the name of TOI 849b, TOI TESS Object of Interest. So it was some time ago that I think they found this. You're quite right, where our numbers are well up in the thousands now. It passed 4,000. I think it was about a year last March when we passed 4,000. So it's well above that now. Anyway, TOI 849b surprised people because it's a relatively large object. It's an easy one to observe because it goes round its parent star once every 18 hours. That's its year. Once every 18 hours. And so, you don't need to observe over a very long period of time to catch many transits of the planet in front of its star. And that means you can refine its orbit very well. You can get a really good idea of its diameter, and it's basically a Neptune-sized object in its diameter,
which would automatically make you think gas giant.
That's right. Yes, exactly. So and Neptune-sized objects are interesting, but this is even more interesting because it's right near the parent star. Normally, you don't find Neptune-sized objects right next door to the parent star. Sometimes you find hot Jupiters, things that are bigger than Neptune, but not anything of this size. So that already made it interesting. But then the real clincher was when the second part of the research was carried out, because as you know, if you've got a planet that's going around a star and you're looking at it in the orbital plane, which you have to be for it to pass in front of the parent star and dim the light, it also makes finding its mass easier because you can measure the Doppler wobble of the parent star. You can actually look at the way the planet is pulling its parent star out of place using a spectrograph that breaks up the light into the rainbow colors and lets you see the barcode of information, which includes information on velocity, what we call the radial velocity. So astronomers did that. They measured the amount of wobble that the star was participating in because of the planet orbiting around it. And having done that, they could determine the mass of the planet. And that was the big surprise. Because it is 39.1 times the mass of the Earth. And that, when you combine it with its known diameter from the transit method, basically gives you a density which is very similar to the Earth's density. It's 5.2 grams per cubic centimetre.
So they're saying this is a rocky planet.
Yeah, exactly. It's a rocky planet. It's something
as big as a gas giant.
But as big as one of the smaller gas giants. So 2.3 times the mass of Neptune, a little smaller diameter than Neptune, and a density the same as the Earth. And that is a puzzle. It's not the most massive planet that's been discovered, but it's the most massive for its size, which means it's very dense. So it's a rocky planet. And that is where, the puzzle starts there. It's near its parent star. The comment that one of the researchers has made is that we don't normally see planets with this mass at these short orbital periods. And short orbital period tells you it's close to its parent star. And that leads to the suspicion that it's basically what we're seeing is the naked core of a gas giant planet. So it's a gas planet, kind of like Jupiter, but whose atmosphere has been stripped off. And it may be just where it is in its solar system that has done that, because the surface temperature is estimated to be 1,530 degrees Celsius, which translates to 2,780 degrees Fahrenheit. It's very hot because it's so close to its parent star. And so the thinking is that has caused the atmosphere to evaporate and essentially become this naked gas giant core. Apparently, when you do the calculations, the loss of atmosphere that you would get from that heating it's not enough to account for the fact that this has got no atmosphere at all. So people are suggesting that maybe other events have played a part, maybe collisions with other large bodies in that solar system, which we haven't found. Or one is another interesting suggestion that it maybe started forming as a gas giant, but something prevented that from carrying on. Maybe there wasn't enough gas left in the disk, the protoplanetary disk around the star, or maybe there was a gap in the disk where something else had already formed, where there wasn't much gas to become an atmosphere, and so the
sort of like your partner taking your blanket in the middle of the night, so it missed out.
It's a very good analogy, Andrew. That's right. Yeah. If your blanket's gone, you can't form an atmosphere around yourself. And that's basically what may have happened. So there are all these theories. And I think what's happening now is that astronomers are going to try and make more detailed observations of this object, TOI 849b. to try and find out one way or the other whether it's a gas giant that's been stripped of its atmosphere or a failed gas giant, one that never got its atmosphere. Very, very interesting. And there's a nice quote actually from the lead author. It's a first, telling us that planets like this exist and can be found. We have the opportunity to look at the core of a planet in a way that we can't do in our own solar system. There are still big open questions about the nature of Jupiter's core, for example. So strange and unusual exoplanets like this give a window into planet formation that we have no other way to explore. Very nice quote.
Yeah, indeed. And yes, as he said, we've always wondered about what's going on down in the core of Jupiter and even Neptune and Saturn. This may be not the total answer, but it gives us maybe some better ideas if we study it as to what's happening in the gas giants in our solar system.
Exactly. That's exactly right. So that's how we do it. We look at other solar systems to find out what's happening in ours. It's paradoxical, really, isn't it?
It is, yeah. Why not? I mean, it's the first of its kind to be found. As you say, there are probably others out there, but this is the first one. So at the present time, it is unique.
Exactly. Yeah, very good.
In the future, it may not be very unique.
You'll get letters. People will write in.
I know. Yes. All right. That's a fascinating one. All right. Well, hopefully there'll be more to learn, and maybe they'll tell us some more down the track. This is the Space Nuts podcast. Andrew Dunkley here with Fred Watson.
0G, and I feel fine.
Space Nuts.
Now, as I've mentioned many, many times, we have a new URL so that it's easy to find us and listen, spacenutspodcast.com. Now, you'll probably notice as soon as you type that into your browser and press enter, it changes the URL immediately. That is completely normal. So just for the sake of simplicity at your end, spacenutspodcast.com will get you to our bytes.com site, which is, where the messy URL will pop up. But don't worry about that. That's our problem. Once you get there, it's all wide open. All the episodes are there listed in chronological order. And you can read the blog. You can read the Astronomy Daily, which just updates stories all the time about astronomical and space science news. There's the shop. There's the bookshop. You can subscribe to our service through the page, and you can click on the AMA tab, which I'm just about to do, and voila, be a part of the show. And if you've got a device that's got a microphone in it, you can just hit the start recording button and wham, bam, thank you, ma'am. Tell us who you are and ask us your question. That's as easy as it gets. So you can send us audio questions via our website, spacenutspodcast.com. Now, Fred, it is question time, and we've got a couple of questions to go through. The first one is from John Carter of Mars. Now, I called him that before. I'm sure we've heard from John previously. Hi, Fred and Andrew. Wasn't sure if this question has been asked before, for I listen to all your podcasts and life gets in the way and I miss parts. Well, yes, that's true. I miss them too. I often hear there are 100 billion galaxies or 300 or whatever visible galaxies. Would it be fair to say you can't put a number on it, for it must go on for an eternity? For it to end doesn't seem possible. For if there's a barrier or wall of some description, there has to be something on the other side of that wall or barrier. Even if there's nothing, it's still something. John Carter. It's more of a statement, but it's an interesting analysis to make. Can you put an absolute number statistically on the number of stars, the number of planets, the number of galaxies, the number of black holes, the number of whatever in the universe? And I would think, generally speaking, no, but you could have a pretty good guess.
Yeah, that's right. So you can put a number on what's in the observable universe, certainly as far as things like galaxies are concerned, because this is the conundrum. We think that the universe is very big, And in fact, exactly as John says, it may be infinite. It may go on and on for eternity. In other words, there's no boundary to it. That is a possibility. However, there is only a limited amount of it that we can see, and that's because it's very like being on the ocean. You've got a horizon around you, and you can see to the horizon, and you can see everything as far as the horizon, but you know that there's a lot beyond the horizon that you're not seeing. And that's basically the way it works with the universe. I mean, the obvious horizon is that we look back so far in time that we're seeing the flash of the Big Bang. So we're kind of in a bubble of visibility, which is bounded by a look back time corresponding to the flash of the Big Bang. And you can't see any further than that, because that is looking back to a time when the universe was blindingly bright. So that's just one example of a horizon that you can't penetrate, at least not with electromagnetic radiation. You might be able to penetrate that with gravitational waves. That's something we've spoken about from time to time. So what you can say is, okay, there's a horizon beyond which we can't see. What's the number of galaxies, for example, within that horizon? And the answer is, the answer comes from measurements made mostly with the Hubble telescope, which is, in many regards, at least at the moment, the most sensitive detector we have for galaxies at very great distances. And what you can do is you can look at an area of sky with the Hubble, you count the number of galaxies in that area of sky, excuse me, and then you extrapolate that then to the whole sky. And the number comes out to be about 2 trillion, 2,000 billion galaxies, which are in what we would call the observable universe. But beyond the observable universe, the bits that we can't see, it's kind of anybody's guess. As I said, we really don't know how far the universe extends for. So it is. This is stuff very much at the limits of knowledge. We can get an idea from the Big Bang, the flash of the Big Bang, when we look at what's called the cosmic microwave background radiation, this microwave hiss across the whole sky. Looking at the details of that lets you work out the fractions of different kind of components that the universe has. So you can say it's something like 75% dark energy, 20% dark matter, 5% normal matter, very, very roughly. And that actually gave rise to the story we had a few weeks ago, where the amount of normal matter that was being predicted within the universe was found not to be enough, but a discovery was made using fast radio bursts that it actually is the rarefied gas between the galaxies. So you can work out those proportions, but it's a lot harder to give an absolute number on the total content of the universe because of the horizons that I've explained. They're really interesting.
And that makes perfect sense. I mean, we cannot see the edge of the universe. We know it's expanding, and it's expanding, we think, uniformly, and it's getting faster. We don't know what's driving that. Is there something beyond the edge of the universe, if there is indeed an edge of the universe? That's all pure speculation. I mean, I don't know if we'll ever be in a position one day to figure it out, because the more we sit and wonder, the further away it gets. And it's moving at a rate of knots.
Yeah, exactly. As always.
Yes, but we thank you for your question, John. We know how many are in the visible universe, but who knows what's beyond that. Now, let's move on to a question from Ben Harper. Hi, guys. Ben from Perth here. Love the show. I have another question about black holes. I know another one, but it's one that no one seems to talk about. I was watching a documentary about supermassive black holes at the center of galaxies, and they were explaining that quasars in the very early universe were, in fact, supermassive black holes that were very active. But at this stage in the universe, there had not been enough time for a star to form a black hole then that black holes to grow into supermassive black holes. They then started talking about the idea of direct collapse black holes, a gas cloud so big that when it collapses, it goes straight past forming a star and then turns into a supermassive black hole. I was wondering why no one talks about direct collapse black holes. Is the idea not well known, or is it not very well accepted by the scientific community? Thank you, guys. Love the podcast. Love the question, Ben.
Yeah.
Fred and I had a quick chat about it before we started the show, and we both agreed that it has not been asked of us before, and I can't say that I'd heard of it before, but I'm sure Fred has.
It is, yeah. It's a something that isn't well talked about. Ben's absolutely right. I think it is probably fair, rather than saying it's not very well accepted, not well known or not well accepted by the scientific community, I think it's fair to say that it's fairly speculative still at the moment, that there really isn't quite enough information to put this together. So the story is, Andrew, that exactly as Ben says, that yes, we see quasars in the early universe, quasars, highly energetic cores of young galaxies, and the energy source is a supermassive black hole at the center of these things, which is accreting material in a dramatic rate, and as it does that, it spits out all this energy. And so the conundrum is, you need maybe 1 million or 1 billion solar masses to do this, to make a quasar. But we see these quasars when the universe was very, very young. And the current best theory for how you make supermassive black holes is you start off with a small one and it gradually subsumes other black holes to build over time into a supermassive black hole, a big one. And so the conundrum is that there hasn't been enough time in the history of the universe at the epoch that these quasars are operating for that process to happen. The quasars are evidence of supermassive holes too soon in the universe for the normal accretion process to be working. And so the idea of a direct collapse gas cloud has been proposed. And in fact, there's actually quite a lot of work on it out there, dating back about 2.5 years. There was a theoretical study published in March 2017, which suggests a mechanism that lets you produce direct collapse black holes. So the problem is that if you've got a gas cloud, an enormous gas cloud, it will tend to fragment into smaller clumps, and then each of those clumps will collapse to form a star. So you've got this kind of clumping process, which would have to be absent in a direct collapse black hole. It would have to essentially be fairly homogeneous throughout and simply collapse what's being called a monolithic collapse of a huge amount of gas into that single structure, and gravity just pulls it in. And the theory shows that you could get maybe 1 million solar mass black holes by this method if you could stop the thing fragmenting. And so the theory suggests a mechanism for that, which is that if you have another cloud of gas next to the one that you're talking about, another gas cloud that behaves normally and collapses it fragments its contents into smaller clumps, which then collapse into stars. Those stars themselves emit huge amounts of radiation because they are themselves massive stars. They're 100 times the mass of the sun. And so there's a whole lot of ultraviolet light radiation comes out of that normally forming galaxy, basically, these stars forming in the gas cloud. And the suggestion is that if the other one, the direct collapse one, is near enough to the normal one, then the radiation coming from the normal one will actually inhibit the fragmentation of the big one, and it will basically just collapse into a single supermassive black hole. That's one of the possible theories. It's very, very interesting stuff. And, Ben's absolutely right. It's not talked about enough. It's amazing that we've been rattling on for 3 years or 4 years, however many it is. And we've never covered direct collapse black holes. So thank you very much for raising it. And we will put it on our radar. And if there is new research on it, we'll certainly bring it up.
Yeah. I suppose the fact that it's pure theory is a reason why it sort of doesn't get a lot of airtime, to use the radio terminology. But if the time comes when such a situation is discovered, it would be a huge find, I would imagine.
Well, that's right, and in fact, there are candidates for that having happened. Basically, clouds of gas that are radiating and suddenly disappear. There's I think at least 2 examples of that, and one of them was reported only a couple of weeks ago. And I suspect these 2 stories are linked. That if you have, it was being touted as a disappearing star, a star that had essentially probably collapsed to a black hole without going through a supernova explosion, which is a bit like the idea of a direct collapse supermassive black hole. Sorry, I'm getting my words tangled up here. That story came from the European Southern Observatory about a fortnight ago, and I think it's on a smaller scale, but it may be the same sort of process, that if you've got a large cloud of gas, under unusual conditions, you can get this collapse down to a black hole without it going through the normal processes of black hole creation. It's fantastic stuff.
Oh, indeed. Yeah. Thanks, Ben. Great question. Really worth investigating. And you never know, we might hear more about it in the not too distant future, especially if they can identify with some certainty that, yes, that black hole happened this way. Yep. We will watch and wait and hope. Thank you, Ben. Thank you to everyone who sends us questions. We certainly encourage those, whether you send an audio question via the website or if you just want to message us through Facebook or email us through our website, spacenutspodcast.com. We're going to have to wrap it up, Fred. When we talk to you again, you will be partially mechanical.
I will. I'll be the bionic knee person, yeah. Hopefully.
He's getting a new knee. Is it your left or your right?
It's the left one.
The left one.
Yes.
Okay.
The left knee.
He's got a dicky knee and he needs a new one.
It's been bone on bone for about 3 or 4 years, Andrew. So it's kind of... And
that explains the crunching noise as well.
Yeah. You thought it was bits of paper rattling on the microphone. No, it's the crunching knee.
Oh, dear. See, they did try to tell you in school, sit still, Fred. You just didn't listen.
No, I didn't listen. That's right.
Too busy gazing at the stars. Fred, thank you. We'll catch you real soon.
Sounds good, Andrew, and all the very best to you too.
Fred Watson, astronomer at large, part of the team here at the Space Nuts podcast. Don't forget to follow us on your favourite social media platform. We're on Twitter, we're on Facebook, we're on YouTube, we're on Instagram. And on Facebook, you can even join the Space Nuts podcast group, which is basically fans of the Space Nuts podcast who get together to talk to each other. So look for that as well, Space Nuts podcast group, or follow us on any of your favourite space social media platforms. And we've got some bonus material coming up for you as well. If you're a patron, that will be hitting the respective patron and Supercast platforms real soon. Until next time, thanks for joining us on this edition of the Space Nuts podcast.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.